Alright, in this video, we'll take what we've learned in the last one through an example and try to make it more precise, more mathematical. So let's try to describe the setup for Markov chains. Alright, so we have a sequence of events. For example, this election, next election, the election after that, and we'll be looking at what's going on in each. So we have a sequence of events. And we're going to ask that the number of possible outcomes of the events are fixed. So in each election, there were only two parties, liberals and conservatives, and we're just looking at how a person votes. So each event has a fixed number of outcomes possible as m possible outcomes. So in our case, m was 2. These outcomes are called states. And then, when you want to move from one event to the next, the odds of ending in any particular state only depend on where you started from in the last one, not in 20 things down. If you're conservative in this election, the odds of being conservative in the next one depend only on being conservative here. You don't need to know where the person voted 3 elections ago or anything of the sort. So let's phrase this. At each event, the probability of ending up in a state depends only on outcome of the previous state. Previous event, sorry. I'm getting my words confused. Alright, so we have states, we have events, and this is a restriction on the type of problems that you can look at. Alright, so once you have a Markov chain, once you have these three things, a series of events, a fixed set of outcomes that are the same for each of the event, and a probability of ending up in each outcome that depend only on the previous state, nothing before matters. Alright, so then we'll be able to define a transition matrix. Alright, so if we have a Markov chains with, let me use the same number of states, m states. Then my matrix P, I'm going to call it a transition matrix because it tells you how to transition from one event to the next. So the transition matrix P is an m by m matrix where P of ij is the probability So let me draw it because this is really a bit strange, but otherwise the multiplication would be worse. So ij, I is the row, and j is the column. So if you remember, j was the current state, and that number here is the future state. So this is starting state, and this is ending state. So Pij, which would be this element here, will be the probability of, I want to use the right wording, is the probability of the next event being in state I, given that the current event is in state J. All right, so that's the transition matrix. And then we need the vectors as well, so let's call them xi arrow, like I said, and they're going to be called state vectors. So the state vector will be a column vector just like this, where each of the entries are giving you the probability of being in one of the states. So where xi is the probability of being in state I. All right, so that's called a state vector. And one thing to note, well, I'll tell you two things. First, since these are probability and they are disjoint, there's no way of being in two states, and on top of it, they cover all the possible events, also all the possible states. What you have is x1 plus x2 plus xm. That will be 100%. It covers all the cases, so they should add up to 1. And so because of this, we are going to call x a probability vector. Second thing is if you look at a column here, then you have one fixed starting state and you look at all potential outcome. So second, each column of P adds up to 1. So each column would in fact be a probability vector as well. All right, and what we we've learned looking at the examples that we can use P and state vectors to simplify our computation and keep track of all the possibilities. So if I'm currently in a certain state vector, alright, so that's the current state vector. Then after one iteration, so the next event, well, we can compute all the probabilities of the next event being in state 1, state 2, state 3 in one computation. We can compute its state vector by multiplying by P. And then the one after that, so the second, the phrasing is a bit strange. The event after that will have state vector well, it will be P of x1 because it only depends on the state that you're in right before. And if I replace x1 by this, I'll get P squared of x0. And finally, the nth next event. So in n events from now, we'll have state vector xn, which is P to the n x0. Alright, so by multiplying by P repeatedly, you'll be able to compute the odds of ending up in any event at any point in the future. And we'll see even in the past.